Hey folks, it's T2sday. This is going to be another long one, I'm afraid today, like 20 minutes. We're on YouTube. Let's start with an unboxing video. Uh-uh. All right. Can't have an unboxing without a box.
How you doing, sir?
Okay. Ancient craftsman drill. These cables. AI connectivity is unbelievable. Up here, we're getting to first power on sequence. In fact, that's where we're at. We've got a incredibly ancient VGA monitor. I don't know, I guess I'll just do it. The fan started up, so all right, so here we go. Okay, now we have blue light. They did say that we might have up to like 10 minutes or something on first post. Oh my God, look at this. So we've got bubbles. And we've got air circulating in the reservoir. Is that what this is called? I don't even know. Oh, and now we've got the monitor lighting up and stuff is happening. Or there was stuff happening. Oh, look at this. I'm not going to run any of this stuff, but it looks fine. All right, well, hey, step by step. That's it for now. And today we are live, and the quiet box is running quietly over there, and that's what I've been doing for the last week and a half. What I want to talk about today is mostly what I've learned so far and the reactions, and also just the general idea of what Tenstorrent is trying to do. So got a ton to talk about, so like I said, it'll probably go a bit long. The goals for today were baby P4 events. Now, did I really do that or not? Well, it kind of depends on what baby means. In the Tenstorrent lingo, these tiny little RISC-V processors, the black hole chips, are just lousy with them. There's hundreds of them on the chip, and they call the little collections of them baby RISC-Vs. So if baby P4 events means running on the baby RISC-Vs that are on the 10-zix tiles on the black hole chips, I did not achieve that. If we're talking about running RISC-V code to do minimal events in a standalone little bit of code running in a cross compiler, so it's running in the RISC-V architecture, well, I did do that. But have the black hole Quietbox. Yeah, it's here. Begin playing with it. I've been doing it a lot. I have been having huge fun. I've been having so much fun. I've been feeling a little guilty. In fact, this is the old kind of master of the universe feeling that you get with deterministic computing, that I get with deterministic computing, where, debugging is a struggle, but it's a game of solitaire that you always win in the end, and so forth. I did not do Ulam. We're going to have to figure that out. Okay, so unboxing and setup, we did it. What I want to do today is talk about this, the architecture, my reactions to the Quietbox and Black Hole and Tenstorrent's efforts in general, in this concept of connecting the gap between what you have and what you want, and the various ways that you can think about doing that. And then I want to save enough time to actually try to do a live demo, since one of the main purposes of getting into all of this new architecture stuff is so that we can try to run stuff quick. And if it's going to take time lapse across weeks like it did with the T2 tiles, then we don't want to do that. We want to push that away and figure out how to do as much as we can while still having it move along enough that just looking at it would be interesting. Is this scientifically important? I'm not sure. But is it practically important? It is in its way. Okay. Mind the gap. So I've been saying since the very first, the pilot episode of these T2sday updates, I've been saying a whole new stack. That what we need is a whole new stack. So much so I got a button for it finally. From hardware to software to systems to artificial creatures, who knows? Tenstorrent is a company after my own heart because, in essence, that's what they're trying to do, too. They're trying to go all the way from silicon, brand new silicon, with a lot of architectural changes. I mean, the individual pieces of architecture are all familiar. It's not doing anything super exotic computationally, but putting it together into an architecture that's got a lot of complexity, a lot of details, and trying to get to something useful from there. And the question is, in all of these cases, how do you bridge the gap? The gap, in my mind, there's tons of ways to look at it. They're all related. They're all about implementation. Things that could exist, things that could persist. I mean, you can build all kinds of stuff, and I have built all kinds of stuff that fell apart quite shortly. And the bridge between things that could exist and the things that could persist is life. That's the living computation presumption, that what makes something life is that it does work to persist. And similarly, things that we make versus things that make money. That's what business is supposed to connect, or a successful business. Once again, you can easily make things that do not make money. I can exemplify that as well. But it's essentially the same concept. Things that we could have, things that we could want. So the Tenstorrent approach, as far as I basically understand it, now this may have involved a pivot somewhere along the way, but whatever, to build these new machine designs in silicon and roll them out and win at machine learning. So in particular, take some market share away from the gorilla in the room, which is NVIDIA, doing this, and so Tenstorrent has stuff like this up on their website, and this is all of the AI models, Llama, Stable Diffusion, all of these things that people at the company or people out in the outside world have brought up on various generations of Tenstorrent hardware, and they're trying to make it as clicky as possible. That you want to try Llama 3.1, 70 billion parameters. Well, you can do that. Here you go. And so on. And so that's an approach. That's the fundamental approach that they're trying to do to to bridge the gap between this new architecture and, well, in this case, what people know, which is SIMD, the thing that NVIDIA uses to MIMD or MISD or various other things that Tenstorrent is using. And the main trick they're using to try to bridge this gap is open source. And they're putting all this stuff out there, which is, it's tough. It's risky. I mean, when I first started doing open source, I was kind of ashamed of the quality of my code, and I am still kind of ashamed of the quality of my code, but so is everybody's code sucks. I mean, there's occasional absolutely beautiful pieces for several different notions of beauty, but most of it out there is not, and it's more important to get it out there and let people share it or not as they will. So, in particular, the software base that Tenstorrent is producing has this thing called Metallium or TT Metal, Tenstorrent Metal, and then there's all of the stuff absolutely down at the, it's close to the hardware as you can get. You read the hardware specs and you write C in assembler code. Now, the funny thing from my point of view is that on the Tenstorrent marketing point of view, they talk about TT Metal as being a low-level interface, because a high-level interface from their point of view is clicky and get a large language model, clicky, get ChatGPT one day or whatever it happens to be. And the Tenstorrent Metallium level is low level relative to that, but it's really high level compared to going all the way down to the silicon. And on the Tenstorrent Discord, there are two extremely competent developers that will answer questions from open source developers and schmoes such as me. Marty1885 is way up, again, from my point of view, way up at the TT Metal point of view. Corsix is all the way down at the read the hardware description level, and I was facing, I was LibComp, that's me, was in the gap, and to some degree I'm still in the gap, and which way should I go? And so I explored them over the last week and a half. At first I was looking, let's go down low level because we're cool, we're really talented hackers, we want to know what we can exploit, let's go low level. Well, so I downloaded some of Corsix's demos and started working through them, and it was like, holy crap. The upper level, the TT Metal stuff, has, a user mode driver that is supposed to talk to the kernel mode driver and make things much easier. In the Corsix code, we'll just write our own thin user mode drivers. That's all we need. Similarly, Corsix has no problem not only putting assembly language in comments, but actual binary code inside the C code. And, where's this come from? Not my problem. And, blah, 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 set up the PCI bus with the reconfiguring the bar 0 for the TLB. We could do this. There's code to do this, but we prefer to do it ourselves. And it was like, I couldn't even read half the acronyms in this comment when I first started. I know about TLBs from base CPU architecture, but not in the context of PCIe. I am a newbie in PCIe. And all of this terrified me. So I said, okay, let's go for TT. Let's go for some hand-holding. And so I started doing demos there, and it was good. There was, I could get stuff going a lot quicker. But, it's all these things about, the assumptions that the code base makes are not quite the assumptions that one wants. And there's a lot of people who are in this boat, and they are, doing things like saying, how does this particular thing work? And Marty1885, this is a not uncommon kind of response. That is a fairly low-level AI. What do you want to achieve with it that's not viable with the higher level ones? And, trying to push people up higher, keep them away from Corsix. And of course, my problem is what I want to do is not machine learning. I don't care about machine learning. I did machine learning in the 80s. I care about artificial life. So That's not the answer that I'm looking for. And then it gets tougher. What is the solution for the following error? Somebody asks. And the answer is the kernel is larger than what we allow. Now, kernel is what I would call program. If it's your kernel, if it's your program, make it smaller. That's the advice. Make it smaller. What limit are we talking about here? We're talking about a limit of under 8 kbytes. If your program is more than 8 kbytes, it's too big. And it's like, Now, again, for what they're trying to do, the point is putting lots of code on the baby RISC-Vs is not what it's about. The baby RISC-Vs are just supposed to be simple controllers to drive these piles of matrix multipliers and all kinds of floating point stuff and so on. But I'm not doing that. And I own a Blackhole Quietbox. So I pushed back towards Corsic, so I bit the bullet, and I've been doing all this bottom-up stuff, trying to figure out as much as I can, trying to simplify it as much as I can, tear the code apart, move it into various classes and stuff like that, so that maybe I can make it more general. And that's where we're at. And so I want to take a couple of minutes, and then we're already running long, but if we say 20 minutes, we're okay, to show you a little bit about running some code on the Quietbox, on the Blackhole architecture right now. So here we are. First, I want to show you some of their code, TTSMI. This is their telemetry. Well, this is their system management interface, Tenstorrent system management interface, but the telemetry is the most fun. So we've got device number 0123. Those are the 4 black hole cards in the Quietbox. So each of those rows has got hundreds of baby RISC-Vs organized in all crazy ways, and all of those cables that you saw me putting in that we're hopping between are connecting those different 4 devices to each other so they could speak to each other. I haven't tried any of that yet. It's they're running at 4 volts. They're running at 3/4 of a volt, but 50 amps. So if we scroll over, so each one of them is using like 35 to 40 watts to do nothing, just to keep the lights on. The temperature is at 110, 114 degrees Fahrenheit, and it's got this nice little heartbeat going back and forth, like Knight Rider and stuff like that. So that's cool. And and the AI clock is running at 800 megahertz. That's its slow rate. It cranks up to 1.3 gigahertz when it's actually got business to attend to. And so TTSMI is really nice, but as an example of the challenges of the whole thing, when you try to run your own code, now you want to look at the core temperature and the AI clock and see that the core temperature is going up and the AI clock is 1.3 gigahertz. It doesn't work, because at the moment you cannot run, at least as far, I've had no success. You can't run a TTSMI at the same time that you're running other code that has the Tenstorrent devices open, as far as I can tell. And that's an example of what happens when you're trying to build a whole new stack, but as a result, you have so long to go from silicon to machine learning that, that all of the layers that you put on, they're not very all that well, pounded out, so that the convenience features aren't really there. Okay, but nonetheless, it's useful. All right, so here's my code. I'm going to recompile it. Let's, whoops, that's not what I wanted. That's not what I wanted either. That's what I wanted. All right, so we'll delete everything, and we'll go again. So now this is taking some time to compile there. The rest of it's going to go very rapidly once it finishes this compile. All right, it built the online code. It sent it out. It ran. It closed. We're done. So that's an example of where we're at, and this is the kind of spikes, simple little programs that I've been writing for the last week and a half to try to learn how to use all this stuff. And the most important single bit of it is that we've got this, that we actually have debuggability, debug printing, coming from at this point just the one particular Tensix tile on each of the boards, but there it is. So we can launch code, and the code that we launch, where is it? Here it is. This is the important point. I'm launching code that's a half a meg. in size, not 7 kilobytes. And most of that half a meg is a complete waste that I just wrote to fill up space just to make sure this would work, but it does. Okay, so that's the state of the spikes. Our goals for next time is to have actual baby P4s, meaning running on the baby RISC-Vs on the Tenstorrent tiles. Lots and lots of spikes, trying out lots of stuff. I have, does this work? Yeah, I guess it does. I have a new to-do list for myself where I have spread stuff all around. So we want to, I would like to get this BMC access, P4 events, there it is down there, and so forth. We'll see how it goes from there. And that is it. Thanks so much for checking in whenever you did. I hope to see you next time.